All right, now we're going to be talking about nuclear chemistry and radioisotopes. Radioisotopes, atoms with unstable nuclei emitting radiations. Couple of words in here very important that you need to know, besides, writing in your nuclei and writing in your radiations. This word will be used in phrasing of a lot of the questions. Emitting, an emission, okay, or which one emits a particle. You see that word? Basically what we're talking about here is that it's being shot off of the nucleus of the atom. It's coming off the nucleus, okay? It's leaving the nucleus. So when you see or hear the word emit, emitting, emission, just make sure that you are paying attention to what that means now, because yes, like I said, it will be phrased in a lot of the questions. Now before we continue going through lots of the notes here, we're going to get a little bit overall background about nuclear chemistry and the uses of it, and kind of understanding the pros and cons here and what we're talking about. Elements with atomic number greater than 83 are radioisotopes, unstable nuclei, and they are considered to be radioactive. This will kind of be touched on again later on, but elements with the atomic number that are less than 83 have isotopes that are usually stable. And there's very rare ones that pop up in these smaller atoms, smaller elements, that can be radioactive, like carbon-14 is one of those examples. We have carbon-12, which is very stable, and the majority of the abundance of carbon. But carbon-14 has 8 neutrons and 6 protons, and it is a radioisotope. It's used in carbon dating, radioactive dating, to figure out the age of fossils. So, and then, every time you eat a banana, you're eating just a tad bit of a radioisotope of potassium, because potassium exists in like 4 different isotopes, and one of them is radioactive and unstable. But it's a very minute amount, very small amount, so it's not like it's going to really affect you in terms of being exposed to extra radiation. Next class, we're also going to do a checklist and see how much radiation we are getting exposed to on a daily basis. Now, things where you're going to find nuclear chemistry important, like medicine. Radio tracers, iodine 131, iron 59. If you go to the hospital, okay, and they need to do some kind of scan, and I've actually had to do this twice, one in high school, and once a couple years ago when they did my MRI, the one in high school, I had to drink this stuff, and it puts the radioactive isotope in you, so when they put you in the machine, then certain things that need to glow are going to glow, and they can figure out where your injury is. For the MRI, they had to put the contrast in. They did it intravenously, so they stuck a needle in my vein, and was able to ascertain and look at and have the right contrasting things on the MRI that they needed to see in order to diagnose the condition. Okay, so yes, it does bring pictures up, as you can see on the screen, giving you a better idea, and they can look at and see different symptoms based off of the scans. Another example of this shown here, when they do the PET scans, cause gamma ray emissions that are then detected by the ray of sensors around the patient, and they can help diagnose lots of different conditions like brain cancer, schizophrenia, epilepsy. And up here, this nice picture showing you a normal brain on the left here, and the Alzheimer dementia brain over here on the right, and they obviously have different appearances in the coloring pattern, okay? And then, of course, the doctor can order more tests if they need to explore some areas, or, they go with that diagnosis. So medicine's good, uses lots of nuclear in hospitals too. A lot of the doctors, especially the radiologists and technicians that work in there, they have to wear badges and things and watch how much they get exposed to, and they always wear those like vests that have the lead in it so that they are not exposing themselves to the extra radiation. Another thing, like I was just saying, it's used in dating, archaeology, geology, looking at fossils. Carbon-14 is a big one. Okay, so this is another use of the nuclear, being able to date fossils, looking at half-lives of different components in different samples. So it's also very helpful when we're looking here in this arena. Now, carbon-14 has a half-life of about 5,700 years, so they can date things that are hundreds, thousands of years old, and looking for that organic material that's going to contain the carbon. Carbon-14 does undergo beta decay, which is a special type of radiation, into nitrogen-14. So we'll be looking at that particular radiation today. Cobalt-60 and some other types of radioisotopes are used for eradicating the microbes and looking at keeping food from spoiling, from decomposing from the microbes. So if they, hit it with some radiation, and sometimes they do this with like UV light too, be able to kill some of the stuff that would start decomposing the materials, such here as in the picture, like strawberries, and allow them to last a little bit longer, because obviously that can be very expensive, but the gamma rays will kill the bacteria and allow them to last a little bit longer. We do get exposed every day to different forms of radiation. Going to the dentist, usually get them once a year where they x-ray your teeth. And we have to concern ourselves about radon. Radon comes out of the ground. Okay, it's produced when uranium-238 decays. If you have basements, and sometimes the basement foundations can have cracks in them, and that's when you need to have a radon detector downstairs in the basement. Now up here in Northern Virginia, I don't know how many people have basements. A lot of people don't, some people do. But you would probably want to, if you have a basement, to have a radon detector down there, because obviously, if you can see, we're in kind of a high area, the green-blue area where this takes place. Now, radon can decay and produce polonium. Polonium then, if we're breathing it in or if we're exposed to it, can damage cells. So it's a very, very common thing, as you can see, in a lot of different areas of the United States, because radon levels will be high, and uranium is, in the soil, and it's mined there, and so obviously these things can occur. Now we're going to go into more of the notes here, nuclear reactions, but first of all, let's talk about the difference of nuclear reactions and chemical reactions. Chemical reactions involve the electrons, the bonding, the covalent or the transferring of electrons. That is a totally different realm of chemistry than what we're talking about today. Nuclear reactions involve a change in the atom's nucleus. The protons and the neutron numbers are what are going to change, and that is going to change the overall element that we're talking about. So for nuclear reactions, we're not really focusing at all on the electron cloud. We will be focusing on changes that occur in the nucleus of the atom. Protons and those neutrons there. That's what we need to be concerning ourselves as we're going along. Do remember that the number of protons in the nucleus determines the identity of the atom. So if we alter or change the proton number, now we have a new element. It's no longer the element that it once was. So I'll be using these phrases a lot today about we're going to start with a parent atom, and then after the decay occurs, we'll have daughter atoms. Just like in biology, before mitosis, it was considered the parent cell, and after mitosis, you came out with two daughter cells. This case, you're going to have just one daughter atom, but it will be kind of the same language that we'll be using here. Stability of the nucleus depends on its proton to neutron ratio. So we'll be comparing the proton numbers with the neutron numbers to determine how stable the nucleus is going to be. And you'll notice here on your graph, which we're going to see on the next slide, that there are certain ratios that are more stable than others. Small atoms, atomic number less than 20, are stable when the proton to neutron ratio is about 1 to 1. Looking at that ratio being about 1 to 1. Larger atoms, okay, those ones are looking for a 1.5, 1 to 1 ratio of neutrons to protons. You can see on our graph here at the beginning, we're really 1 to 1 down here. Then the band of stability veers off from the 1 to 1 ratio line, and it becomes more of a like 1.5 to 1 ratio. And as they get larger, they get more neutrons in comparison to the number of protons. And as they get more larger and that ratio increases, then the instability starts to occur. Okay? So as you get up there, it wants to establish that 1.5 to 1 ratio and be right around there. Typically and it will undergo decay until it actually reaches that some sort of stability in that range. Okay? So we say nuclei with atomic numbers greater than 83 are radioactive. Elements with atomic numbers of 83 and less have isotopes that can be radioactive, but they're usually in very small percent abundances. Now, Becquerel discovered that radioactive atoms undergo significant changes and it alters the identity of the atom. The unstable nuclei lose energy by emitting the radiation, but it is a spontaneous process. And if you think about a spontaneous process like that, you're going from something that is unstable to something that wants to achieve stability, so it just is going to happen. Doesn't need or require energy to do so. And when it does happen, a burst of energy comes off when the particle breaks off or the gamma ray does. And that's because, if you think about it, in the nucleus, there has to be some kind of really, really strong force holding all those protons close together. Because protons are all positively charged particles, right? So if they're all right next to each other, they should be repelling each other, but there's some really, really strong force holding them all together. And when you break that force, here you get this huge amount of energy in that reaction, okay? And this is what you're going to be seeing, this kind of picture here. This is really the picture of the nucleus. The red and the gray are representing protons or neutrons. And then an actual particle breaks off and emits from the nucleus, or if it's gamma, it'll just be pure energy. And then you get a new atom, you get your new daughter atom out of it. It's no longer going to be the same as it was before. So they try to stabilize, the nucleus will lose protons and neutrons and transform into a new element. As it transforms into that new daughter element. Radioactive decay. Rutherford messed around with this because he was doing his gold foil experiment and he was using radioactive material in his lead block and shooting it at the gold foil. And in this process, he, all of his experimentation found that uranium compounds were producing 3 types of radiation. Those 3 types of radiation were alpha, beta, and gamma. And he named them as such, so they follow the Greek letter system. He also found that they had different penetrating abilities. They weren't all equal. So he separated them into the alpha, beta, gamma categories, and that's what we'll be looking at today. If you kind of remember his kind of gold foil setup, it's the same idea here, except for he had his piece of gold foil over here. But he had the radioactive material in the lead block and shot the alpha particles at the gold foil, but here just kind of set up to go through the electric field. By going through the electric field, the positive plate and the negative plate, as you see the positive plate above and the negative plate below, the different types of radiation are going to have a tendency to go towards the certain charge that is opposite of what they have. So in that electric field now, The beta particles, which have a negative charge, they kind of veer or skew towards the positive plate. Well, we know that because positive charges attract negative charges, so that would make sense. The alpha particles are going to go the other direction towards the negative plate because they're positive, so they're going to want to attract to the negative plate. And the last type of radiation, gamma, goes straight through because gamma is neutral and does not have a charge. I will be going over and comparing these in the table below, yes. But keep in mind, this was kind of the experimentation that Rutherford was doing and was able to see these results from. Alpha decay. Now we're going to go through the chart in a minute, but you can kind of, as we're going along, fill a lot of it in. Like for instance, in alpha decay, the nucleus emits an alpha particle. What is an alpha particle? Well, an alpha particle is essentially 2 protons and 2 neutrons. 2 protons and 2 neutrons. That means it has a positive 2 charge because it has 2 protons in it. That also means 2 protons and 2 neutrons is equivalent to a helium-4 nucleus. Helium has a mass of 4 and it has 2 protons, then that must mean it has 2 protons and 2 neutrons. The only thing that's missing, an alpha particle is a helium nucleus, is the electrons. The electrons aren't there, so it's not a helium atom, essentially a helium ion. That's what an alpha particle is. But we don't call them helium ions, we call them alpha particles, by the way. Alpha radiation can be stopped by a sheet of paper. It can also be stopped by clothing. It has very low penetrating ability. Then we use a nuclear equation in order to show how this is going to work. So let me describe what this equation looks like because we're going to do some example problems later. On the left side of an arrow, we typically call that the reactant side, or what are you starting with? That's the starting material. The arrow indicates some kind of reaction occurs. In this case, it's going to be a nuclear reaction, not a chemical reaction. On the right-hand side are the products of the reaction. And we use this notation to denote what an alpha particle should look like in the reaction. You can also write it with the alpha symbol, and you might see it written this way. The alpha symbol kind of is like a fish, Greek letter. Okay, you might see that. Either or, you can represent it. If you're denoting an alpha particle, you can put it in either form. You can use HE or you can use the alpha symbol. What you should notice about both sides of the arrow here, because matter is not created or destroyed, it is just simply changed, is if we start with a mass of 238 over here, then that means the mass over here that gets released should also equal 238. They can be in separate forms, but 234 plus 4 is 238. So those numbers should add up on either side of the equation. The other thing you should notice too is that the atomic number, or proton number, does change with an alpha particle. 2 protons are lost. So we're no longer, if we have uranium 238 and an alpha particle breaks off of it, it's no longer uranium, it now becomes thorium. And you see that right here, thorium 234 is the daughter element out of that. Beta decay. Beta radiation consists of beta particles. Beta particles have a charge of -1 because they are a high-speed electron that shoots off the nucleus. The thing to note about beta decay has a transformation that occurs in the nucleus. You have 1 neutron in the nucleus. 1 neutron actually changes physically into a proton and an electron. A little piece breaks off. The electron has barely any mass. The proton actually sticks around in the nucleus, doesn't leave. The only thing that shoots off or emits from the nucleus is the high-speed electron. But because you have a neutron changing into a proton and an electron, that proton now changes the element. We no longer have the same element. So this is what comes off of the nucleus. the electron. The proton sticks around, changes the proton number. The mass number is going to remain the same because the neutron that you lost was now replaced by the proton, so the mass number doesn't change. So beta decay has a little bit going on there. And you can use aluminum foil or metal foil to stop beta particles. You can also use wood, blocks of wood. Beta particles have a moderate penetrating power. And here's our nuclear reaction example. Over here, if you're starting with thorium-234, you would end up getting Pa out of it, 234, and here is your beta particle. And you can write beta particles like this as well, 0 with the -1 and then with the beta symbol, and it's like a B with a little tail. I don't write Greek symbols very well, but you get the idea. If you see the B, you know it goes with the beta particle. I personally like using the electron notation because it is a high-speed electron. So when I do it, I always use the electron notation. But you might see this on your paper as such, and you should recognize it as a beta particle. Okay? The last type of radiation, well, no, actually this is the third type of radiation. We've got a couple more to go. Gamma radiation, high energy radiation that possesses no mass, no electrical charge. It is basically pure energy, pure electromagnetic radiation energy. It's very high penetrating, it's at very short wavelengths, and lots of energy. This is the kind of stuff that causes cancer and radiation poisoning. Bad stuff. Don't want to go near it. And no, we don't get to all turn into the Hulk, apparently. Instead, we mostly, if we're exposed to too much gamma radiation, would get cancer and die. Yes, so big green monster, no, probably not going to happen. They are massless, so they don't really change the element at all. However, what you'll see with gamma is usually gamma accompanies or is part of one where an alpha particle or a beta particle breaks off. You'll see a gamma ray also coming off in that process. So these guys usually happen with alpha and beta decay. They don't happen typically on their own. Okay? And this is the kind of stuff that, the nuclear waste and, the Chernobyl event that happened in the 80s, this kind of fallout is still there. Can't even live within, I don't know, like 100 miles of the place because it's very, very contaminated. So that's the trouble with nuclear. The nuclear power plants are good. It's very clean energy, but what do you do with the waste product? Or what do you do if you have a meltdown or explosion due to some kind of inadequacy in the nuclear power plant cooling process? Okay? This one can be stopped by lead, and it can be stopped by concrete. And nuclear power plants are built out of lots of concrete for this very reason. But you also know and have seen probably at the dentist, they put those vests on you with the heavy lead in it, or if you've gone to get an x-ray for a bone or something, and they typically will put, if it's an arm, they'll put something around the rest of your body so they only are zapping the arm with the radiation. Okay? Shielding, penetration, this is just a visual aid to help you understand. Alpha particles, not very penetrating, they get stopped by paper or clothing. Beta particles, a little bit more penetrating, moderate, will be stopped by foil or wood, and then gamma will be stopped by lots of concrete or, several millimeters of lead. Okay? So now let's go ahead and write in our chart the information, if you haven't already. Composition of alpha decay is going to be an alpha particle, 2 protons, 2 neutrons. So you can write that in here too. 2 protons, 2 neutrons. It's a helium nucleus. It has a charge of +2, and it has relatively low penetrating power, and you can write clothing in here too, because it can also be stopped by clothing. Beta decay, beta particles, they are high-speed electrons. So I always like to note that too, that they are not regular speed, they are high speed electrons. That's why they have a little bit more penetrating power. They have a little bit more energy than normal electrons. Have a -1 charge and moderate penetrating power. And you can also note here that it can be stopped by wood, blocks of wood. Last but not least, our lovely gamma radiation. Our gamma symbol is a Y, it looks like a Y. High energy electromagnetic radiation, which is just pure energy. There is no charge on it, and it has relatively very high penetrating power, which can be stopped by lead or concrete. Now we're going to be looking at some actual problems. Radioactive decay. So radioactive decay, like we said before, is represented using the arrow, and you have the parent atom on the left, you have the daughter atom on the right, along with the particle that was emitted. This particular case, the first one, we started with polonium-210, and it lost 2 protons and 2 neutrons and turned into lead-206, and ended up with the helium nucleus or the alpha particle being emitted. You could also have written it like this, just to tell you, with the lovely, oh, it didn't erase. There we go. Now we can erase it, and using the alpha symbol instead. Beta decay. Here we're showing the carbon-14 undergoing beta decay. One neutron transforms into a proton in the nucleus. That's why it went up to 7. And shot off the electron that also came off in that. And therefore you have your beta particle on the right-hand side, along with nitrogen-14. Remember, you can also write beta like this. 0, -1 with the tail and the beta symbol. Now for gamma. This particular example is very good because it shows you that gamma accompanies an alpha or a beta. In this case, uranium-238 gave off an alpha particle, and in the process here comes a gamma ray with it. The gamma ray is the funny looking Y symbol there, 0, 0 representing no mass or no charge. So this right here is showing you your gamma that accompanied the alpha over here. Okay, usually it doesn't happen on its own. It's usually a part of a beta or alpha decay. Okay? So let's look at some practice now. Before we get to the practice, let's look at positron emission. There were 2 other types that I need to talk about. Positron is a special one because it's a particle with the same mass as an electron, but it's positively charged, so it's kind of an opposite electron. That's the best way to describe it. It's a positive electron because it is about the same size and mass of the electron. What happens here with positron emission and electron capture, I'm just going to give you the generalized idea. Electron capture and positron emission occur when the proton number is too high. Proton ratio part is out of whack. Too many protons in comparison to your neutrons. So it's kind of opposite of beta decay. Instead of the neutron changing into a proton and electron, now you're going to be starting with the proton here. And it is going to break off and form a neutron. But it also, in that process, breaks off and forms this positive, little tiny positive that flies off the nucleus and emits from the nucleus. So the proton changes over into a neutron and a positron. Positron is like the electron in the fact that it's the same size, but it's really just a positive, fast-moving positive thing. Okay, not very big. And what it does here, if you look at this particular example, it is going to take 1 out of the proton number and reduce it. And when it does that, you go from sodium, which is 11, to neon, which is 10 in terms of the protons. Now you can write positrons like this too. You can write it like this with the plus and then the B, because it's like an opposite beta particle. Or you can also write it like this, with the 0 plus 1 in the E, because it's like an opposite electron. So you might see positron particles looking like that. Either or is okay. Now, positron emission also occurs more often in the lower elements, the smaller elements, whereas electron capture occurs in elements that are a little bit higher up in terms of their protons to neutrons. This is the only time where you're going to actually see the particle on the left-hand side is when you have electron capture. Particles on the left-hand side with the parent atom here. Okay? And essentially what happens in these proton-rich nuclei is the element itself like takes in an electron from its cloud and encompasses it into the nucleus. It combines with one of the protons and forms a neutron in that respect. Once again, reducing the proton number. The idea of positron and electron capture is to reduce the proton number to achieve stability. So it takes in an electron, so you can use the beta particle to represent that because the beta particle is representing an electron. But it goes on the left-hand side. Still make the numbers add up just like you would before. And in this process is showing us that mercury 201 turns into gold 201, and it also gave off a gamma ray in the process. But it took in an electron, changed that, and combined with a proton, and it turned into a neutron. So that's also why the mass number does not change, because the proton that was lost is now in there as a neutron, so the mass number stays the same. And that electron it steals from is usually one closer to the nucleus, because it can easily be encompassed or put into the nucleus. So here is our electron capture. You can represent it as the beta particle. So let's do some examples here. Looking at this where they left the blank, what should go there in the blank? What will make the numbers add up correctly? The 4-2 alpha particle. Very good. You could write it like that with the helium, or you could write it with the alpha symbol. But we can fill in the blanks because we need to make sure the numbers add up. So that's how we can determine which type of radiation is going to go in there. So the thorium-234 plus the 4 gives us the 238 on the left-hand side. The 92 for uranium, we have 90 plus the 2 that's in the alpha particle, so that adds up correctly. This also has a gamma here. We have gamma. You know, this one, of course, represents the alpha. Now, you might be given things like this in order to write them out. You will have, they give you the parent atom, like here we have americium 241, and we're going to do an alpha decay with it. So what I do to set these up is I write my parent over here, 241, and AM, and I look at my periodic table. What is the atomic number of americium? 95. Okay, so it's going to undergo an alpha decay, so I put in my alpha particle here. And then I can just do my subtraction. It's very easy. What's 241 minus 4?
Oh. 237.
237 is my new mass number. What's 95 minus 2? 93. And what is my new element then? Neptunium, or NP. Good. And that's how you could write out that particular decay. Now let's look at doing the beta decay of iodine 131. Once again, I would start over here by putting my parent in. I have I 131, and iodine is what, 53? Okay, so it's going to undergo a beta. I like to use the electron rotation myself. So something plus 0 gives me 131. That's pretty easy. What's that? 131 is the mass number. Now don't get this backwards, because something plus minus 1 gives me 53. So it must be 54, and 54 is which element? Xenon, very good. Xe. Okay, so those are some examples of how you would write out those reactions, those nuclear reactions. Try this one for positron emission of antimony. 120, antimony 120. Antimony is what atomic number? 51. And it's positron emission, so we're going to give off the positive version of the electron, the positron. So now looking at the numbers, what should be up top here? 120, and what should be below here? 50, good, because 50 plus 51 gives me antimony. And 50 is 10, right? Sn. Correct? And let's look at below at our electron capture. What do I need to remember about this one?
It's the only one that has a particle.
Only one that has a particle on the left side. We need to stick the electron on the left side. So we have gold, 195. Gold is 79, right? Okay, good. So we need to add in our electron over here, which is a beta particle. So I just use the electron version of it. And then what are we going to get out of this? 195 and 78. What is 78 on the periodic table? Platinum, PT, very good. So this would be writing an equation for electron capture. So, what? It doesn't tell me that there's a gamma involved. If it told me there was a gamma involved, yes, I would add it in. In this particular case, it doesn't tell me that there was also accompanied a gamma radiation accompanied this process. So if it does tell you, say, this part of, or this particular atom undergoes alpha decay and also gives off a gamma ray, then you would write it both in. If it doesn't tell you to do that, then you keep it off, okay? So you don't automatically just stick in gamma rays. You have to see if it tells you to put them in there, okay? Now let's talk about fusion versus fission. Two different types of energy releasing reactions in which energy is released from the nucleus. The protons and neutrons collectively, they're called nucleons. That's another vocab word you might want to note. Nucleons. You see that? It's referring to the protons and neutrons in the nucleus. Now nuclear fission is you're taking a larger atom. Here in the picture, as you see, a larger atom, and it breaks down into smaller atoms. The nuclear fusion, you take two smaller atoms and it combines to form a larger atom. They're kind of opposite each other. Fission versus fusion. Now, these produce a lot of energy. Like I said before, the binding energy, that's this very strong force that holds those protons together. So when some of it breaks off, it does release a lot of energy in the process. So we can get a lot of good, usable energy out of nuclear, and it's harnessable. However, nuclear does come with that, with the drawbacks of the waste product afterward. What do you do with all that nuclear and radioactive material? And you also face, the occasional environmental disaster if anything happens to the nuclear power plants, like Fukushima with the tsunami. Definitely, caused a lot of problems. They had meltdowns and explosions because the coolant system was disrupted by the tsunami. Chernobyl, where the plutonium was unstable and it, blew. You can't live in that area anytime soon. And it's already been like 30 years after that happened, and still you can't go near. It's very contaminated. So there are some drawbacks to using it and putting it in nuclear power plants, but it's safe if it can be maintained. Now fusion, on the other hand, fusion would be a great concept, but fusion usually needs like 40 million Kelvin in order to work, so it really needs to happen at very, very, very high temperatures. And, you know, we can't really sustain those kind of temperatures and keep it, be able to harness it and keep it stable. You can do fusion bombs, but you don't really care. You're trying to blow something up. You're not trying to harness it and keep it, you know, within check. Fission, nuclear power plants, they use the neutron. They usually use uranium-238, 235. Those are used in the nuclear power plants. They send neutrons to hit the uranium, which causes it to break down and undergo decay. And then once that uranium breaks apart, it also gives off 3 more neutrons. So it sets up this thing called a chain reaction, where that will keep sustaining. And eventually, like if you let it go and you had a good amount of uranium, you would get a pretty big explosion out of it. But in the nuclear power plants, they have these control rods that they use to stop the amounts of the neutrons so that they keep the reaction under control. So it does bombard the uranium atoms and it does keep the process repeating. But like I said, there is a critical mass point where, you know, it can get very explosive, but in the nuclear power plants, they have control systems in place to keep that from happening. But if something disrupts their system, like say a tsunami, then we have issues and you have the meltdowns and explosions that can occur. And it does produce a lot of electricity, and it doesn't give us the byproducts of burning fossil fuels, so it is technically cleaner than some of that other fuel source that we get energy from. But like I said, afterwards, what do you do with the waste product that is still radioactive? Nobody wants to live near that. Can be, you know, what do you do with it? Put it in drums, bury it in the mountains, but in Yucca Mountain out in Nevada somewhere. I believe it's out in Nevada. They store a lot of stuff out there, but you wouldn't catch me moving there and living anywhere near that mountain. And they used to do a lot of nuclear testing in Nevada and in New Mexico, so I, you know, probably wouldn't want to live near that either. Nuclear fusion. This is what happens in the sun. 2 hydrogens, basically the sun is a ball of hydrogen. 2 hydrogens combine to form a helium, and in that process gives off lots of energy. And this is how stars work. They're doing fusion. And it can sustain that 40 million Kelvin or whatever ridiculously high temperature it is. And gives off vast amount of energy. The problem here, like I said, is we can't really control 40 million Kelvin and keep it sustaining and be able to harness it. That's way too hot. So what we need is people like you to study fusion and come up with a way to do it at lower temperatures, and that's what is referred to as cold fusion. So hasn't been done yet, something to think about. Cold fusion would be a wonderful energy source if we could have fusion at lower temperatures and then be able to produce lots of energy that's clean and doesn't hurt the environment. So the reaction there, I think at the bottom of your page, is showing the hydrogens combining into helium, and that's what actually happens in our sun. Good? So we're going to start the decay series in just a minute.